So we can start with the first presentation. I
Okay.
think with the Shema. Okay.
Yes, so thank you, Professor Stefan, for answering all the questions. Thank you, Dr. Isi, also for assisting us. So we will now begin our second part of the event,
Yes.
and we will welcome Shema Hamid, who is a PhD candidate in theoretical chemistry from Al Manar University, Tunisia, of course. And she will present a talk. She will present a talk titled "Impact of Decorated Cobalt 0001 Catalysis Surface on the Amination Reaction of Deoxyribonucleic." Sorry for the pronunciation. And by DFT study.
Yes. So we have
So
15 minutes. Yeah.
okay.
Okay, so good evening, everybody. My name is Shay Mohamed. I am a PhD student at the University of Tunis, El Manar, and UNES de Lyon. Today, I will be presenting a theoretical study entitled Impact of Decorated Cobalt 001 Catalyst Surface on the Amination Reaction of Dihydroxyacetone, and I do a DFT study. So this work sets the intersection of green chemistry by biomass valorization and computational catalysis. I hope to take you through the key steps that led us to some very encouraging findings. Let's get started. So let me start by placing this work in context. The broader project is called GLINANO, which stands for one-pod selective amination of glycerol using ligand-decorated metal nanoparticles. The ultimate goal is to move toward bio-based amines, molecules that are extremely useful in pharmaceuticals, agrochemicals, and material science. Why glycerol? Because it's cheap and abundant, and is a major byproduct of the biodiesel industry. Transforming it into value-added amines using a sustainable pathway is therefore highly attractive from both economic and environmental perspectives. So what makes this reaction particularly clean is that water is the only byproduct. And now the key challenge is selectivity. So glycerol has multiple hydroxyl groups, and we need to control which one will react to the surface and how. So that is where the design to bespoke catalyst, in this case, cobalt nanoparticles, becomes critical. And this is exactly what this study addresses computationally. Before going any further, I want to acknowledge that this work is linked to our recently published article, the reference of which you will find here. So I encourage you to look it up, just to see the dehydrogenation process. Let me now describe our computational methodology. So we use density functional theory as a main tool. DFT is a theoretical approach that allows us to calculate the electronical structure of atoms and molecules, and in our case, the interaction with the surface and the adsorbate, with a good accuracy, of course, and a tractable cost. Our methodology rested on three pillars. First, the geometry optimization. We optimize the molecular structures of all species involved. This will give us the most stable configurations and tells us where and how the molecule will adsorb to the surface. activation barrier. For each elementary step in the reaction, we calculated the activation energy, essentially the energy hell that the molecule have to overcome for the reaction to proceed. And this is a fundamental for understanding which steps are the rate-limiting steps. And third is identifying the reaction intermediates by mapping out the full energy profile step by step. And then we were able to characterize all the intermediates. Now, let me talk about the reaction. So the reaction mechanism is already proposed in literature by our group. So there's two pathways. Either we are going to do the amination, and there's two transition states. Either the hydrogen will bond to carbon first, and then bond to the nitrogen, or vice versa. Means it will bond to the nitrogen first, and then the carbon. A key question here, at this stage, of course, which of these pathways is actually preferred on the cobalt surface? So on this slide, we can see the full reaction mechanism mapped out with all the elementary steps. You can see the imine adsorbed here. Sorry, here the imine adsorbed. And then the first path is where there is the formation of the first bond carbon hydrogen, then the intermediate obtained, then the next transition state till the amine. And the second path is the same thing till the amine. These are the distances are resulted with our DFT work. To determine which pathway is kinetically preferred, we looked at two key criteria. First, the activation barrier, and second, the adsorption energy. A more negative adsorption energy means a stronger binding to the surface, which can stabilize intermediates and favor certain pathways. By combining these two criteria across both pathways, we were able to identify the blue sequence, which is the favorable mechanism for the obtention of the amine. So basically, on the cobalt, the first bond formation is the carbon hydrogen and then the nitrogen hydrogen to obtain the final amine. This slide will summarize the amination reaction pathway here on the clean surface of cobalt. So this part of the work, we already published it, first one here. This is already published in our article. Then it follows the equilibrium. The amination at the equilibrium is an approach done by our group and already published it too. And then this temperature of 453.50 Kelvin is the typical experimental conditions for this type of transformation. So the energy profile shows the complete pathway from the adsorption of the imine till the formation of the amine. You can see also the sequence of the intermediates and the transition states. And this will serve as a reference system to our next work. So now the natural question is, what happens when we decorate the cobalt surface with acetate ligands? And that is precisely the question we ask. What would be the impact of acetate ligands on the catalytic activity of the surface catalyst? In experiments, cobalt nanoparticles are often coated with organic ligands In this case, we'll use acetates. These ligands are known to influence the surface chemistry, but their precise effect is not very studied. So our DFT approach gives us a unique opportunity to answer this question. We first need to understand how the acetate ligand itself behaves on the cobalt-001 surface. The important phenomena are shown here first. The conformational change. So we can see that the conformer of the imine change when there's ligands on the surface, and then the formation of hydrogen bonds. The hydrogen bonds are not covalent interactions, but they are significant enough to influence the geometry and stability of intermediates. So both of these effects probably captured in the model before we can calculate the reaction pathway on the decorated surface. This slide just, I put all the reaction mechanism when there is the ligands on the surface. You can see the interaction of the imine and the intermediates, also the transition states with the surrounding ligands. Now we come to the central result of the study. This slide shows the emanation reaction on the coated surface also at the same temperature. So, sorry. Differences become immediately apparent. So the presence of the acetate ligands modified the relative energy of several intermediates and transition states. In particular, some key steps which were energetically costly on the clean surface become more accessible on the decorated one. This is a direct computational evidence that ligand decoration is not just a passive effect. It actively reshapes the energy landscape of the reaction and in a favorable direction. To quantify the overall impact of the catalytic activity, we use the concept called energy span. So it's a theoretical framework that provides a single number capturing the kinetic efficiency of a catalyst cycle. The energy span is essentially the energy difference between the highest point and the lowest point of the catalytic cycle, taking into account the direction of the mechanism. A smaller energy span means a faster and more efficient catalyst. Our calculations show that the energy span is reduced on the acetate decorated surface compared to the bare one. And this translates directly a predicted enhancement of the catalytic activity. This is a key result. So basically, the ligand decoration does not just modify the surface, it actually improves the kinetics of the emanation reaction. Sorry. Let me now summarize the main findings. Using DFT calculations, we identified the most favorable reaction pathway for the emanation hydrogenation of the dihydroxyacetone on the cobalt-001 surface, and we established the complete reaction mechanism leading to the amine formation. This work provides atomic scale understanding of how ligands assist cobalt catalysts in the context of biomass derived amine. It demonstrates a promising and sustainable route toward amine production using DHA. To summarize, decoration works, and now we understand why at the atomic level. Of course, this is not the end. This is just the starting point. We will see the same reaction on the open facet of cobalt 1120 because real nanoparticles expose multiple facets, so this comparison is crucial. Second, we will investigate further amination transformations toward nitrogen-containing products. And we aim to explore kinetic effects under realistic operating conditions. Before I close, I would like to thank the people who made this work possible. This project has been a truly collaborative effect, and I'm deeply grateful to my supervisors in Tunisia, my supervisor Karim Michel in UNS de Lyon, and our experimental group at Université de Poitiers et Université Paris-Cité. I would also thank the Arab Science Network for this opportunity and Dr. Aris for his help and his good work. And thank you all for attending.
Thank you, Dr. Shema, for your clear presentation, for your precious, for your precious work. We hope that the listener enjoyed your presentation. So, as usual, we will read some of the questions.
Yes.
Okay, from the comments. So the first question is technical, I guess. It was about how I can get VASP software. It's technical question. I think.
Okay, VASP.
Okay, VASP, yes.
Yes, it's a online, I think, but I don't know if it's available like freely. I think you have to pay to get it. I think so. So for me, I have the platform of PSMN because I am linked to the University of UNS de Lyon. So I use the shell they gave me.
Okay. The second question is from Iman Jouabi. She's interested on DFT studies. I mean, on DFT study of metal oxide nanoparticles.
Oxide,
If you
yes.
can advise me, she's asking for some advices.
Iman, are you a master or a PhD student? We don't have. Okay.
Yeah.
So basically, oxides for now is titanium oxide, and I'm already working on one article now with Colorado University. So basically now it's like the field is interested in titanium oxide. So if you have work, you can just use that oxide and yeah, you'll be fine.
Okay. The next question is from Sarah Bouzidi. She's asking about why did you choose DFT modeling for this study?
Okay, DFT is used specifically for the periodic systems. So, I mean, I just took a slab and do the reaction, but we have to put in mind that this, to be realistic, it have to be periodic. So just, we have to imagine that it will be on a very big slide. Just put, for the DFT, it can just put a small slide and give you the same as experimental results.
Okay. We have another question.
Yes.
I think we will take 2 or 3 more questions, and sorry for the other participants. So the previous question is asked about Aisha Hassan. She is thanking you, of course, and she wants to ask why was glycerol specifically chosen for this dihydrogenation study? And
Okay,
could this computational approach be extended to other biomass derived molecular?
Yes. So first, glycerol is something abundant in nature, and I think the organic team can just talk about glycerol more than us. And second is because it's not actually investigated a lot in literature. It's something that it's new and that we can work on it and just we can explore more. So it's something really there's no such papers on it and on the dehydrogenation of it, because it's just very big molecule and needs a lot of work.
Okay, so I think we'll take one more last question. Okay. So in your DFT study, which cobalt surface sits turned out to be the most active for the reactions, and how does the surface structure influence it?
Okay, so certainly I always refer to literature. For literature, they always use the decorated nanoparticles of cobalt, because cobalt is a transition metal. It's good, but it needs enhancement. So either we alloy it to something or we decorate it with organic ligands. For me, in the whole thesis, I used a compact CFC cobalt 111 surface, and for the hexagonal compact, I used 001 cobalt and 1120 cobalt. So I used 3 surfaces.
Okay, I guess due to time
Yes, of course.
we will pass to the to our second speaker. We want to thank you, Mrs. Shaima, for your presentation again and for answering all the questions. Thanks again to the to the participant also. So, Mrs. Fatima Tahiri, can you please open okay, open your camera, okay, and share with us your screen. Thank you.
Does it okay now?
Okay.
Sorry, Fatimata. Sorry, Mohamed. Before, I'm very sorry. I have to leave. I cannot stay until the end. So just a few words to say thank you to everyone. It was really a nice pleasure.
Thank you again,
Thank you.
Stefan. Thank you for
See you.
and see you.
See you, and good luck
Thank
for
you.
all the students for their future and for opportunities. See you. Bye.
Thank you, Stefan.
Thank
Bye.
you. Thank you.
Thank you. Bye.
Okay, so we are welcoming Mrs. Fatima Tahiri. She's a PhD student in computational chemistry, specializing also in DFT, and she will talk about the theoretical investigations of oxazole-based materials for atmospheric pollutant capture. She's from the University of Ibn Zahr University from Agadir, Morocco. So you have, it's up to you. Okay, you have the mic.
You see my is it okay now? Could you hear me,
Yes,
please? And full screen is does it show?
yes, yes, of course.
Okay, good evening to everyone. My name is Fatima Tahiri and I'm a doctoral researcher at Ibn Zahr University in Morocco. Today I will present my work on theoretical investigation of oxazole material for atmospheric pollutant. So to get you through my talk, I will begin with introduction, then present my methodology and result and discussion, then end with conclusion and perspective. So, air pollution is one of the greatest environmental challenges of our time. In fact, every breath we take is affected by it. The main sources are well known, such as industrial, fossil fuels, agriculture, and waste. These activities release greenhouse gases, toxic gases, and fine particulates into the atmosphere. The consequences are serious, such as climate change, smog, acid rain, and significant health problems for millions of people worldwide. This is why developing efficient material to capture and reduce pollutants is too important, and it is motivation behind my research. So, as we all know, several materials have been explored for adsorption. Recently, metal organic frameworks or MOFs have emerged as very promising because of their very large surface area and tunable pore, which give them high adsorption capacity. So, by combining metal nodes with different organic ligands, such as imidazole, amine, and carboxylic acid, their selectivity and gas uptake can be significantly enhanced. Oxazole is another promising heterocyclic compound. However, its potential for CO2 capture has not been yet explored. This open exciting opportunity for developing new materials for gas separation and environmental application. In this work, we investigated the interaction between oxazole and CO2N2, then extended the study to cluster-based system contain gold, copper, and Zn3O3 using computational method. The aim is to evaluate oxazole-based material for gas capture application. So for methodology and theoretical approach, in this work, we studied the interaction of oxazole with CO2 and N2 using accurate ab initio method. Firstly, the geometry of oxazole with CO2 and oxazole interact with N2 complexes, as well as their spectroscopy property optimized using MP2 method. We used the augmented CC advanced triple zeta basis set for two-body system and the double zeta basis set for three-body system, which means cluster when the metal interact with oxazole and CO2. Then the binding energies were first calculated at the MP2 level and then confirmed using high-level CCSD F12B calculation to ensure reliability. And finally, all binding energy were corrected for basic superposition error and 0-point vibrational energy to obtain accurate results. Now moving to the results and discussion. So to simplify discussion of the molecular structure, we labeled the atom of oxazole like what you see here. The nitrogen atom was labeled as number 1. The two neighboring carbon labeled N1 and C2 and C3, and for the oxygen was labeled as O4. And the remaining carbon atom was assigned as C5. Finally, the hydrogen atom were numbered H6, 7, and 8 according to the symmetry of the molecule. Then to examine the molecular level adsorption of CO2 and N2 on oxazole, we first located CO2 and N2, like you see here, at the N1 seat level of oxazole, and then we oriented them around the oxazole. Also here we are the nomination of all possible interaction, like the interaction with N1, it's called E1. For the interaction with side O4, it's called A2. The interaction between oxazole and those gases, if it's up, it's called E3. If it's down, it's called E4. And from this side, it's called E5. Now moving to study the interaction of two-body system. Only the interaction between oxazole CO2 and oxazole N2. We are going to start with the interaction between oxazole and CO2. This study carried out on oxazole and CO2 complex revealed existence of two stable structures labeled E1 and E2. In structure E1, the relative energy it was 0, and the interaction it was between carbon 9 and hydrogen 6, and between carbon from carbon dioxide and nitrogen, and with this distance, of course. And for A2, we have the interaction between O4 with carbon from carbon dioxide, and with hydrogen 8 and oxygen 11 from carbon dioxide, and relative energy it was 1.31 kilocalorie. Additionally, the study of the complex between N2 and oxazole revealed the existence of 4 adsorption states outlined here, like E1A, E1B, E2A, and E5. As figure shown, the interaction this time it was between nitrogen from N2 with for E1 and A for E1A and A2A. The interaction it was between nitrogen and the hydrogen 6, and for E1B and E5. For E1B, the interaction it was between nitrogen and hydrogen 7, and between N2 and hydrogen 8 for the A5 structure, and the relative energy are here. So moving now to the binding energies, our calculation indicates that oxazole is energetically favorable as an adsorbent for both our adsorbents, although CO2 shows a higher capacity to bind oxazole ring. The range for CO2 when it interacts with oxazole, it was between -4.13 to -2.82, and from -1.77 to -1.19 for oxazole interact with N2. Based on the adsorption energies, the nitrogen state of the oxazole is the most stable state for CO2 adsorption, and the hydrogen 6 is the most stable state for N2 adsorption. Also, 0-point vibrational correction range from -3.62 to -2.43 for oxazole CO2, and from -1.38 to -0.85 for oxazole with N2. For BCC correction, it ranged from -4.22 to -2.84 for oxazole CO2, and from -1.72 to -1.14 for oxazole N2. And for the CCSD, it ranged from -3.96 to -2.64 for CO2, and -1.19 to -0.78 for oxazole N2. Now moving to 3-body system. This section examined adsorption and activation of CO2 and N2 on small metal cluster, such as gold, copper, and the metal oxide. We are going to start with interaction of oxazole CO2 with metal. The complex were initially formed by attaching stable structure, namely E1, to the most stable form of gold, Zn3O3, and copper. And the results are shown in this figure of the interaction. So the gold, copper, or zinc atom situated at the apex of the octahedron form a covalent bond interaction with O4 for oxazole. Also, as seen, the gas is physically adsorbed, and the structure of oxazole complex is moderately perturbed by the presence of the cluster. Like we see here, the first lead interaction, it was between this the oxygen and this hydrogen, but here it seems like this bond is broken and there's another bond constructed between the oxygen 11 and the hydrogen 7 for the interaction with gold and the interaction with copper. Now moving to the oxazole N2, we did the same thing for the complex oxazole. We attached stable structure of the complex, namely E1, to the most stable form, gold, Zn3O3, and copper. And these are the optimized structure. It seems also that in the oxazole cluster, the gold-copper are situated at the apex of the octahedron form a covalent bond interaction as the O4 of oxazole, and also here it seems that this bond is broken and another bond is constructed here. Now moving to the binding energy, our cluster shows that metallic and metal oxide cluster favor the adsorption of CO2 and N2 gases. In hexametallic clusters, adsorption energy reach a maximum with copper cluster at -6.46 for oxazole CO2 and -10.25 for oxazole N2. However, the gold and Zn3O3 cluster exhibit similar binding energy value with -4.58 and -4.56. Also here -2.19 and -2.22. This is a highly advantageous as it allows for the replacement of expensive gold cluster with more cost-effective materials such as Zn3O3. So moving to the conclusion, to conclude, the oxazole shows strong adsorption for both CO2 and N2 with higher affinity towards CO2. Also adding gold, copper, and Zn3O3 cluster enhance gas adsorption with the copper 6, showing the best performance. And as a perspective, future work will investigate other gases and organic ligands to improve MOF adsorption performance and selectivity. And before concluding, I would like to acknowledge the support that made this work possible. This research was supported by the European Union Horizon Action Atmos project under grant agreement H2020. I would also like to express my sincere gratitude to Ibn Zohri University and all collaborating institutions and researchers involved in this project for their valuable scientific support and collaboration. Their contribution and guidance greatly supported the progress of the research. And finally, thank you to all of you for your attention, and a special thank to Arab Science Network for this opportunity. I want also to thank Professor Yusri for creating this network, and thank you very much to the team for your guidance and your support, especially to Mr. Mohammed and Ferial and to everyone. Thank you very much.
You, Fatima. Thank you.
Thank you, Mrs. Fatima. It was a well-structured presentation. Hope the participants enjoyed their time, and I mean they enjoyed your presentation. So we will now pass to the questions. Of course, we will read from the comments. So we will take maybe 6 questions, or we will see. We still have some time, so we will take some questions. So the first question is, I think, technical also. She say from Nora bin Hamada. She's saying how you could choose the perfect atom to link.
Firstly, we started by oriented the gases around the oxazole. Then we did our calculation. After that, we did the vibrational analysis, and we verify the frequencies. When we have positive frequencies, it means that those structures are stable and there is no transition state. So we did some calculation, and we decided which one is better.
Okay. The second question is from Ferial Dorban from the ISN. She's thanking you, and she's asking, do you think these materials could be synthesized and tested experimentally in the future?
Yes, of course, our study is theoretical, but the next step would be to synthesize oxazole-based material and test their gas absorption experimentally in using spectroscopy and with using spectroscopy technique, of course. So we hope to do it by myself.
Okay. There is another question about future work or material design. Are there any specific functional groups you want to try next to improve CO2 capture, like amine or hydroxyl groups?
Why not? Yes, I'm thinking to change oxazole with others organic groups, especially heterocyclic. It will be better.
Okay. Another question. What are the main advantages of turning these oxazole-based materials into MOFs for future industrial applications? Okay.
Could you repeat, please, or where is the
Okay.
question? I
So
didn't
the question
understand.
was,
Yeah.
what are the
Mhm.
main advantages
Yeah.
of turning these oxazole-based materials into MOFs?
Into MOFs.
Okay.
MOFs is
Oh,
a metal organic
yes.
frameworks. They're known by their very large surface area and tunable pores. So they are very special for atmospheric pollutants or for capture gases in general. So it is to import. It is something
Okay.
important. Or Mhm.
Okay. Another question from Lina Ahadoun. Among all calculated complexes, which one is expected to be the most experimentally stable?
We found that copper gave a good result. So if we can try experimentally, of course we will start it with the copper.
Okay, so we will take the last question, I guess. One last question. Um, since air contains water vapor, how might H2O affect the ability of your material to capture CO2 and N2, carbon and
Actually, this is one of the next step of my work. I need to try it with with H2O. So I don't know exactly now, but maybe I will have the response soon.
Okay, so thank you, Mrs. Fatima, for your for answering
Thank
the
you.
questions, and sorry
Thank
for
you.
not being able to give you all the questions. I mean, so we will pass to our last participant.
Thank you very
Her
much.
name is okay. Thank you, Fatima. Thank you. Okay. So as I was saying, we will now pass to our last participant, Mrs. Laetitia Zigar. She is aerospace engineer and a PhD candidate in aeronautics from Saad Dahleb University, Blida, from Algeria. Welcome to you, Mrs. Laetitia, and you can start. I mean, you have okay. You can start.
Okay. Good evening, everyone. Thank you, Arab Science Network, for this opportunity. Is my voice clear?
Yes.
Yes. Okay.
Okay. I will share this presentation. Okay, we'll start then. The topic of this presentation is hydrogen peroxide decomposition and investigation of flow and simulation. This work is presented by me, proposed by Monsieur Amel. First, we start by the introduction. The importance of chemical science in rocket science is very crucial. We find the topic of this presentation is a preliminary study of the composition of hydrogen peroxide at high concentrations in system of propulsion in space. We go first by the general context. The general context contains this decomposition, an estimation and an investigation of the reaction. Then we go for the simulation of flow in nozzle, convergent divergent nozzle of a rocket engine. The problem statement. The building of a proper thesis that covers only the experimental investigation. This study shifts focus toward a numerical modeling of the system. Next, we have the motivation. The problem in aerospace engineering is very crucial, this topic. This is allowing us the methodology to be extended to wider ranges of experimental cases. Then we go to objectives. The objectives of this work is to validate the numerical simulation and tools. Also to verify the accuracy of the experimental setup and to ensure the reliability of the laboratory operation conditions. We go here a brief description of the content of this presentation. We have the H2O2 or the hydrogen peroxide decomposition, nozzle flow simulation, and further contribution for this work. First, we start by methodology. We first have here the modeling or the decomposition investigation. Decomposition investigation is made by a program in Fortran, which is known by a scientific programming language used mostly by NASA and very serious states. We have here at the right the complete program that calculates the outputs of the reaction given the concentration of the hydrogen peroxide in the input. Mostly the hydrogen peroxide used in rocket engines is a higher concentrated hydrogen peroxide. So what means from 90% till 100%. We find at the right side, the output of the system is based on 90% hydrogen peroxide because this percentage is the one used by the previous experimental data. We have in the outputs also the product of the reaction and the temperature, the energy, and every thermodynamic parameter. These parameters are used as inputs in the simulation of the flow. We have here now the simulation. The simulation is made by a software is made by an ANSYS software, which is known by simulations and high fidelity approximations to experimental results. For the mathematical modeling, we have at the right side the flow equations, the equations that use to calculate the flow conditions as continuity equations or conservation of mass, and the Navier-Stokes equation. At the left side, we find the turbulence modeling. Since the flow is at a very high velocity and a very mixing form, we have to use very critical turbulence modeling forms. Here we choose a K omega transient phenomenon. We have, which is based on 4 equations, instead the other modeling that are based only on one, as Spalot-Almaras, or 2 equations which describe the kinetic energy and the dissipation or the specific dissipation. This model is very crucial, that captures every shifting in the condition of the flow. Then we go for the geometry. As an input for the geometry, we choose the form that used previously in the experience, which is a convergent divergent nozzle with a ratio of with area ratio from the exhaust over the throat of 100, which is a very thrustful nozzle. At the second image, we find the geometry of the study. The geometry of the study, as we see, is different from the geometry of the nozzle. Why? Because we had to use a far field simulation, a far field part in the simulation to validate the far field pressure, or what we call the atmospheric pressure at the ambient conditions. Because if we had to cut it at the exhaust only as the form of the nozzle, the far field pressure or the atmospheric pressure won't be verified at the exhaust. At the right side, we go for the meshing, or what we call mathematically the discretization. All the geometry is discretized, as we find in the second image, or divided on several cells, which calculates in any cell the parameters of the flow. Now we have here the operating conditions. The operating conditions is set, as we said before, on the previous experience that has been done by the previous researchers. Then we go here for the results and the discussion. We find here at the right side the simulation or the contour given by the ANSYS fluent on the Mach number, or what we defined as the velocity of the flow over the velocity of the sound. As we find here, we find that flow is very close to the real state. Why? As the validation of the analytical data gives us the Mach number goes till 4.9, and the simulation gives us the Mach number goes to 4.83, and the minimum Mach number, which is the inlet Mach number, is 3.26, and it's exactly the same Mach number as the inlet pressure that inlet pressure gives. We find at the left side the static pressure. The static pressure describes us the comportment or the behavior of the flow across this nozzle. This static pressure is given on the nozzle wall, because we simulated, or we had an hypothesis that at any section the conditions are isentropic, are the same at every section. So we took here, as we see, the maximum pressure or the inlet pressure is 25 bars, or 25 times 10⁵ pascals. This pressure is chosen in order to make an optimum flow across the nozzle. As we see, the pressure is very constant at that length. The length that is proposed to make the flow uniform. In order, when it enters the nozzle, the simulation, the assumptions, and the hypotheses are valid. And we have abrupt descendant in pressure, which agrees with the geometry, because the angle of the retracement of the nozzle is 60 degrees, which agrees exactly with the diagram. And then we have the minimum of pressure. The minimum of pressure which coincide with the throat of the nozzle. Why the minimum of pressure coincide with the throat of the nozzle? Because as we have the Hugonian theorem tells that the pressure decreases at the minimum, which is in the throat. At the throat, the number of Mach number will achieve 1 in an optimum nozzle. And we have an increase in pressure. Mostly the pressure has to decrease, but we have here an increase in pressure, which is due to the existence of a shock wave. When a shock wave arrives at the throat, it means that the throat achieved the Mach number, which is 1, and allows the divergent to be supersonic. And we have next that the pressure decreases at the minimum and achieves the atmospheric pressure. That means that the convergent is subsonic, then sonic at the throat, and then supersonic at the exhaust or the divergence of the nozzle, which validates the numerical results here, validates strongly with the 1D analytical solution, which is calculated by the well-known equations of thermodynamics and sections. But also, the simulation is a 2D, and also we have a 3D simulation, also agrees with the same results and the same Mach number and pressure values. Okay. I have here in the conclusion, we have key achievements and contributions in this result. First of all, we have the validation of the analytical models. The validation of analytical models successfully completed a numerical simulation that validates the initial 1D preliminary design approach. Also, we have the complementary to prior work. Since we have the work done before is only an experimental result that doesn't validate by any numerical or any previous other experimental result, so this work adds a significant value to a previous experimental study by modeling the exact same nozzle geometry. Also, we have the software benchmarking. Demonstrated and generalized the stability of ANSYS Fluent as an accurate simulation tool for this class of problems, which means that this work not only validates the experimental results, but also validates the use of the software ANSYS Fluent in this typical case of problems. For future work and further contributions, we have, since this is a very important part in the rocket science engineering, the use of catalytic modeling is very crucial. Why is that? Which is done by previous experiments that validates the optimization of the thrust and the optimization of the specific impulse of a rocket engine used by a catalyze. So, incorporate an actual catalyst bed chemical reactions directly into hydrogen peroxide decomposition process is very important and for future insights in technologies in this 2026. And also we find the hybrid methodology. We have to reinforce the catalytic study using a combined approach of both experimental testing and numerical simulation. Imagine a numerical simulation with experimental data added by a catalyzer is something well demanded by aerospace engineering. We have also advanced turbulence modeling. Why we always ask for advanced turbulence modeling, since turbulence is a very chaotic phenomena, we have always to choose the specific and the very high fidelity tools to simulate this turbulence. Transient to high fidelity turbulence modeling. For example, in our case, we used K omega SST transient, but for higher fidelity, we can use LES or large AD simulation that gives us a very pointed and very exact results, or if it's even possible, the DNS. So we go here. I think we go finally to the final of my presentation. Thank you for your for being in this for assisting this presentation. Special thanks for my institute and every researcher who contributed in this work and still contributing and still working in this field. And also I go for special thanks for the Science Network for this opportunity for the second time, and good luck for further work and further opportunities like this. Thank you.
Thank you.
Thank you very much.
Thank you, Mrs. Leticia, for your presentation again. It's your second participation. We are proud to have such beautiful people and such scientists in our community. I mean, it was very insightful. So we will now answer to some. We will give you some questions, of course, from our participants. So I will give you the first question. Okay. The first question is about a participant is asking, could you give us the program name that you used in your simulation? Okay, technical question.
First, we had used two programs. The first program, which used it for programming, or the program that gives us the investigation of the decomposition, which is Fortran programming language, and for the simulation is ANSYS, specifically ANSYS Workbench or ANSYS Fluent.
Okay. The second question, so in this results, which simulation software or CFD tool did you use to obtain these numerical and validation results? I guess it's the same question, I think.
Yeah, it's the same.
Yeah, so basically you answered it. Yeah.
Yeah.
Okay. Second question. So I want to ask you to ask, can this model be extended to more complex systems? For example, in
Yeah.
3 dimensions or in, I don't know.
Yeah. Actually, for 3D for 3 dimension is a separated work that a couple of groups that are working on that. But in our group, we are working for 2D simulation. We are in collaboration with them, but we're still working in 2D. Our further or large application, yeah, we had a lot of application in that. For example, as we said before, the percentage of hydrogen peroxide is now not only a constant entered in ANSYS Fluent, but is a new input. So you have the program is all ready and the simulation is always ready. So when you have your simulation, just you give it the geometry and you enter your percentage, and it gives you the result and the simulation immediately. You don't have to work from since the beginning, just to follow in the work that's been done before.
Okay. The next question. So we continue with questions. How does your catalysis help keep hydrogen peroxide stable and prevent it from breaking down too fast or becoming dangerous?
First, the use of catalysis in hydrogen peroxide is a very advanced and very demanded technology. Why? Since before, catalysis are used only for acceleration the reaction and optimization the thrust and the specific impulse, as we say in rocket science. But since the new technologies with the new materials, new combinations of materials, and always and specifically the presence of 3D impression. 3D impression allows us for a new specific forms of these catalyzers that allows us to optimize in an astronomic inputs, an astronomic specific impulse of this rocket engines that has never been done before, that couldn't be achieved with previous studies.
Okay, so I guess we will. Okay, there are two remaining questions. Okay, the first one is why have you choose Fortran to develop this computational program instead of Python or MATLAB? Another, technical question.
Yeah, sure. The fourth one is well known as scientific programming language. It's a very critical program. We have that something that which is specific with Fortran is that it has 32. You can have 32 numbers after the comma. We mean that it's very precise. You can, for example, my program is made by double precision, only double precision due to the limitation of my PC. I worked with 8 numbers after, so it's a very critical programming. And since we are searching for very critical results, we don't have the right for a mistake, or as we say, any mistake above 1% is not anymore validated in the field. So it's not the same as Python and MATLAB or other stuff. Even though you're using Python, because only with Python we can integrate AI and we can integrate this in the ANSYS Fluent.
Okay, okay, that was clear, I think. A last question. Moving to real applications, what difficulties do you expect when trying to use this system on a larger, continuous, industrial scale instead of lab conditions? Um,
Yeah, sure. The first problem that we have in this hydrogen peroxide is its own decomposition. The hydrogen peroxide decomposes by its own with the force of time, which we lose the higher efficiency. As we said before, we need a higher concentration above 90%. When it decomposes, it reaches above 70% at a very, very short time. And also we have the pressure requirements. We have the pressure of stagnation, or the pressure that we put in tanks, mostly in satellites, has to be a very high pressure. which is hard for in side of materials and costs of fabrication of things. That's all for the hydrogen peroxide.
Okay, thank you, Mrs. Leticia, for answering all the questions. I mean, and it was very insightful for you. Before we end, I will give the talk to Dr. Yusri in order to close this event.
Yes,
So, okay.
thank you, Dr. Aris. And I would like to thank sincerely all the presenters for their excellent presentations, as well as the participants who attend and followed the different sessions with great interests. So, and we look forward to welcoming you again at future as an event. So, I think in September we'll have a conference in physics. Dr. Eris, yes, in September
It will
or
be
August.
in August, yeah,
In
doctor. In
August,
August,
okay. So in
we will have
August, we'll
our
have, yeah,
yes.
yes, exactly. Okay, so thank you again, and see you, see you in another event. So, bye.
Thank you, Dr.
You.
Yusri. Thank you.